Dear students, myself Thakre Yenar from LVH Junior College, Nimgaon, Taluka Malegaon, Nasik. Students, this is my second video. In first video, we studied electronic configuration of elements of groups 13, 14 and 15. Also, trends in atomic and physical properties of elements. Student, in this second video, we are going to study chemical properties of elements of group 13, 14 and 15. Student, you know that oxidation state. The elements of group 13, 14 and 15 exhibit various oxidation state. The highest oxidation state exhibited by p block element is equal to total number of valence electrons, that is sum of s electrons and p electrons. This is called oxidation state. Beside the element of groups 13, 14 and 15 exhibit other oxidation state which are lower than the group of oxidation state by 2 units. The lower oxidation state become more stable as we go down the group. Students, we saw the chart. Oxidation state of the element of groups 13, 14 and 15. At first we saw group 13 having outer electronic configuration NH2 NP1. Group oxidation state +3. Other oxidation state +1. And some example of stable compound, that is BF3 boron trifluoride, AlCl3 aluminum chloride, GaCl3 gallium trichloride, InCl3 indium chloride, TlBr thallium bromide. Second, that is group 14 having outer electronic configuration NH2 NP2. Group oxidation state +4. Other oxidation state +2 or -4. Some example of stable compounds: CH4 methane, CO2 carbon dioxide, Cl4 carbon tetrachloride, SiCl4 silicon tetrachloride, GeCl4 germanium tetrachloride, SnCl2 tin chloride, PbCl2 lead chloride. And the last group, that is group number 15 having outer electronic configuration NH2 NP3. Group oxidation state +5. Other oxidation state +3 or -3. Some stable example of this compound: N2O5 dinitrogen pentoxide, NH3 ammonia, NF3 nitrogen trifluoride, PH3 phosphine, PCl5 phosphorus pentachloride, ASH3 arsine, SbH3 styrene, SbCl3 antimony trichloride, BiCl3 bismuth chloride. Students, next we saw problem number 9.4. Why thallium plus iron is more stable than thallium plus 3? Let us solve this problem. Solution: thallium is a heavy element which belongs to group 13 of p block. The common oxidation state for this group is 3. In p block, the lower oxidation state is more stable for heavier element due to inert pair effect. Therefore, thallium plus 1 ion is more stable than thallium plus 3 ion. Then we saw bonding in compound of group 13, group 14 and 15 elements. The lighter element in group 13, 14 and 15 have small atomic radii and high ionization enthalpy values. They form covalent bonds with other atoms by overlapping of valence shell orbitals. The first member of these groups belong to second period and do not have d orbital. Boron, carbon and nitrogen cannot expand their octet. The subsequent elements in the group possess vacant d orbital in their valence shell, which can expand their octet form a variety of compounds. Students, next we saw reactivity towards air or oxygen. At first, we saw group 13 elements. Element of group 13 on heating with air or oxygen produce oxide and nitrates. At first, we saw general reaction. 4 element plus 3 O2, it gives 2E2O3. Here E for elements. For example, 4B plus 3O2, it gives 2B2O3, that is boron oxide. Second general reaction, 2 element plus N2, it gives 2En, E for element. Example is 2B plus N2, 2Bn, that is boron nitride. Also group 14 elements. The elements of group 14 on heating in air or oxygen form oxide of the type EO and EO2 according to the stable oxidation state and availability of oxygen. In this group 14 elements, there are general reaction E plus 1/2 O2, it gives EO, E for element. Example, carbon plus 1/2 O2, it gives CO, which are limited supply of oxygen. General reaction number 2, E plus O2, it gives EO2 is equal to element. Example, carbon plus oxygen, it gives carbon dioxide, which is excess of oxygen. As well as we saw group 15 elements. The element of group 15 on heating with oxygen forms oxide of the type of oxide E2O3 and E2O5. Here 4 type of example. The first is P4 plus 3O2, it gives P4O6. Second, P4 plus 5O2, it gives P4O10. Third, AS4 plus 3O2, it gives AS4O6. Fourth, 2Bi plus 3O2, it gives 2Bi2O3. Students, the next point, that is nature of stable oxide of groups 13, 14 and 15. Group 13 element boron oxide B2O3, which is in acidic nature. Second, aluminum oxide Ar2O3, which is amphoteric in nature. Third, gallium Ga2O3, which is also amphoteric in nature. Indium oxide In2O3, which is basic in nature. Thallium Tl2O3, which is basic in nature. And students, the next group 14, first carbon oxide CO2, which is acidic in nature. Second, silicon oxide SiO2, which is also acidic in nature. Third, germanium oxide GeO2, which is also acidic in nature. Fourth, tin SnO2, which is also amphoteric in nature. And last, lead PbO2, which is also amphoteric in nature. And the last group is 15. First, nitrogen oxide N2O5, acidic in nature. Second, phosphorus P2O5, acidic in nature. Third, AS4O6, amphoteric in nature. Sb, antimony Sb2O3, which is also amphoteric in nature. And last, Bi, bismuth Bi2O3, which is also basic in nature. The next point, that is reaction with water. First, most of elements of group 13, 14 and 15 are unaffected by water. Second, aluminum react with hot water, forms hydroxide liberating hydrogen 2Al plus 6H2O, it gives 2AlOH3 plus 3H2. Second, tin react with steam to form oxide liberating hydrogen Sn plus 2H2O, it gives SnO2 plus 3H2. Fourth and last, lead is unaffected by water due to the formation of protective film of oxide. Then the next point, reaction with halogen, group 13. First, all the elements of group 13 expect thallium react directly with halogen to form trihalides, that is EX3. General reaction 2 element plus 3 halogens, it gives 2EX3. For example, 2Al plus 3 Cl2, it gives 2AlCl3. Second, thallium forms monohalide. General reaction 2Tl plus X2, it gives 2TlX. Here X is equal to halogens. An example, 2Tl plus Cl2, it gives 2TlCl. The next, group 14. All the elements of group 14 react directly with halogens to form tetrahalides EX4, where E is equal to elements, X is equal to halogens. Si plus 2Cl2, it gives SiCl4. Second, Ge and Pb form dihalides too, GeCl2, PbCl2. Third, stability of dihalide increase down the group due to enough pair of effect. Fourth, the ionic character of halides increases down the group. And last group, that is group 15. Before this, we saw problem 9.5. GeCl4 is more stable than GeCl2 while PbCl2 is more stable than PbCl4. Explained. Let us solve the problem. Solution. Ge and Pb are the fourth and fifth pairs elements down the group 14. The group oxidation state of group 14 is 4 and stability of other oxidation state lower by 2 units. Increases down the group due to inner pair effect. The stability of the oxidation state 2 is more in Pb than in Ge. And next, group 15. Elements of group 15 react directly with halogens to form two series halide EX3 and EX5. For example, P4 plus 6Cl2, it gives 4PCl3. Second, the pentahalide EX5 are more covalent than trihalide EX3 due to d orbitals of valence shell available for bonding. P4 plus 10Cl2, it gives 4PCl3. In this reaction, nitrogen does not form pentahalide. Student, next we saw problem 9.6. Nitrogen does not form NCl5 or NF5, but phosphorus can. Explain. Let us solve the solution. Phosphorus and other members of the group can make use of d orbitals in their bonding and thus compound MX3 as well as MX5 are formed. Nitrogen cannot form NCl5 or NF6 since it is void of d orbitals in its second shell. And the next point, that is catenation. The property of self-linkage of atoms of an element by covalent bonds to chain and ring is called catenation. Students, the catenation tendency of an element depend upon the strength of bond formed. You know also that among the group 14 elements, carbon shows the maximum tendency for catenation because of stronger carbon-carbon single bond. The order of catenation of group 14 element is carbon greater than silicon greater than germanium is equal to Sn. Lead does not show catenation. This can be clearly seen from the bond enthalpy values. Bond first, carbon-carbon single bond enthalpy 348, silicon-silicon single bond enthalpy 297, germanium single bond enthalpy 260, SN bond enthalpy 240. Students, after that we saw the new point, that is allotropy. When a solid element exists in different crystalline forms with different physical properties such as color, density, melting point, the phenomena is called allotropy, and individual crystalline forms are called allotropes. Student, this is very important point of your examination point of view. And student, the important allotropies of carbon: first, diamond; second, graphite; third, fluorines; fourth, carbon nanotubes; fifth, graphene. The first, that is diamond. Students, in diamond each carbon atom is linked to four other carbon atoms in tetrahedral manner. The carbon-carbon single bond distance is 154 pm. The tetrahedral are linked together, forming a three-dimensional network structure involving strong carbon-carbon single bond. Thus, diamond is hardest nature substance with abnormally high melting point, that is 3930 degrees Celsius. Diamond is bad conductor of electricity. And some uses of diamond. The first use: for cutting glass and in drilling tools, we saw in diagram. And second, for making dies, for drawing thin wire from a metal, which is also seen in PPT. Third, for making jewelry. The next point, that is graphite. Student, you know about graphite. Graphite has two-dimensional sheet-like structure with layers of planar hexagonal rings of carbon atoms. Each carbon atom in hexagonal ring undergoes sp2 hybridization and forms three sigma bonds with three carbon atoms. The carbon-carbon single bond length in graphite is 141.5 pm. The fourth electron in the unhybrid p orbital of each carbon is shared by all carbon atoms. The various layers are held by weak van der Waals forces and the distance between them is 335 pm. Graphite cleaves easily between the layers, hence it is very soft and slippery. Therefore, it is a very good dry lubricant. The electrons in graphite are delocalized over whole sheet due to presence of mobile electrons. Graphite is good conductor of electricity. And important property of graphite: graphite is soft and slippery solid. It is good conductor of electricity. And uses of graphite: graphite is used as dry lubricant in machines running at high temperature. Second use: it is also used as electrodes in electrolytic cell and in electrochemical cell like dry cell. And C, that is fluorines. Students, you know that fluorines is an allotropy of carbon with definite number of carbon atoms. Fluorines are made by heating graphite in an electric arc is an inert atmosphere of argon or helium. The soot form contains mainly carbon 60, fluorine and small amount of other fluorines, carbon 32, carbon 50, carbon 70 and carbon 84. Carbon 60 has a shape like saucer ball and is called Buckminster fluorine or bulky ball. It contains 20 hexagonal and 12 pentagonal fused rings of carbon atoms. The neighboring carbon atoms are at distance of 143.5 pm and 138.3 pm. Fluorine are covalent and soluble in organic solvent. Fluorine carbon 60 react with group first metals forming solid like such as K3C60, which behave as superconductor below 18 Kelvin. It carries electric current with zero resistance. Arrow top are carbon, which is seen in PPT. The fourth is carbon nanotubes. Students, carbon nanotubes are cylindrical in shape, consisting of roll-up graphite sheet. In our syllabus, we have single-wire carbon nanotubes and multi-wire nanotubes. But you also know that double-wire carbon nanotubes and triple-wire carbon nanotubes. Nanotubes can be single-wire SWNT with a diameter less than 1 nanometer or multi-wire with diameter up to 100 nanometer. Their length range from several micrometers to millimeters. Carbon nanotubes are robust. They can be bent and when released spring back to original shape. They have high electrical or heat conductivity and high strain to weight ratio. Researchers at NASA are combining carbon nanotubes with other materials which can be used to build lightweight spacecraft. And the last point, that is graphene. Students, isolated layer of graphite is called graphene. Second, graphene sheet is a two-dimensional solid. Graphene has unique electronic properties. Thank you.